So in this video I'm going to talk about some applications, and let's start with this first example. This is going to be an application of matrix multiplication. So suppose the labor hours for assembly and finishing department for two items are given in matrix L below. So here in matrix L, you know that item A requires 5 hours of assembly and 1.5 hours of finishing. And item B requires 3 hours of assembly and 1 hour of finishing. And then suppose the hourly wages paid for employees in each department is given in matrix W for two different sites. So here we have an assembly department in Arkansas that pays $12 an hour for assembly, and then in Texas they pay $13 an hour. And the finishing department in Arkansas pays $7 per hour, and in Texas they pay $8 per hour. Now what's interesting here is if you multiply these two matrices together in one direction, they don't give you anything helpful, but if you multiply them in another direction, they do give you anything helpful. So let's say I multiply matrix W times matrix L. Alright, so let's take a look at what happens. If you multiply matrix W times matrix L, I'll let you do the multiplication and just show that the result would be 99, 31, 59, and 18.5. But let's just take a look at the first entry, 99. So if we look at the first entry, to get that we would take the $12 an hour given here for the assembly department, and then we would multiply it by the 5 hours for item A in assembly. And so that would give me $60 to assemble item A, to assemble an item A in Arkansas. But then the next entry, 13 times 3, that would be the assembly wages for Texas, but that would be for item B. So that would tell me that it costs $39 to assemble item B in Texas. So what good would it be to take the assembly costs for item A in Arkansas and add it to the assembly costs for item B in Texas? I don't really find much help there by adding these numbers together. But if we turn that around and we multiply W times L, well, now let's look at this first entry. Again, you can check this product and see that you get these values. But if we multiply this, well, then we have 5 times 12. So again, we have the we actually have item A, 5 hours, and $12 for assembly, $12 per hour for assembly. So it shows me that it's going to cost $60. It's going to cost $60 in wages to create item A in assembly. But now look at the second product, 1.5 times 7. And that's going to be how much it costs. That's going to be the number of hours to finish item A times the cost for finishing in Arkansas. So if we add those together, we actually get the total cost for item A in Arkansas is $70.50. Now, if you look at what happens when you multiply it by the next column, you get 5 times 13. So that would be the $5 hours for finishing item A times the $13 per hour in Texas, plus the hour and a half for, the $5 for assembly times the $13 per hour in Texas. So that's $65 to assemble item B in Texas, and then the 1.5 times 8 is 1.5 hours for finishing that same item A in Texas. And then when you add those together, that gives you the total cost for item A in Texas. So the 70.5 is the total cost for item A in Arkansas, and the $77 is the total cost for item A in Texas. And then if you took the second row and multiplied it by each column, that would give you the cost for item B in Arkansas and the total cost for item B in Texas. So that actually would be useful, whereas the multiplying the first product, what I did in the first product when I did WL, that was not very useful. But if you multiply L times W, which that's what this should say right here, it should say L times W. When you do L times W, then the product actually gives you something that makes more sense. Okay, or at least it's practical. It's more practical with that product. And it would even be more practical if we had more items and more locations and more departments. Then it would be a more practical problem. So that's an example of matrix multiplication. Here's another example of matrix multiplication. You have two car dealers, dealer 1 and dealer 2, and you have 4 models, model A, model B, model C, model D. And we know that dealer 1 sold 10 model A's, 5 model B's, 8 model C's, and 3 model D's. Dealer 2 sold 5 model A's, 10 model B's, 6 model C's, and 2 model D's. And this matrix here just represents the revenue. Each model A sells for $12,500, each model B sells for $11,800, each model C sells for $15,900, and each model D sells for $25,300. So if you just multiplied these two matrices together, all it would do, it would take the 10 model A's that dealer 1 sold times their revenue, plus the 5 model B's for dealer 1 times those revenue, plus the 8 model C's they sold times that revenue, plus the 3 model D's they sold plus that revenue, and it would just add up the total revenue for dealer 1. And then when you multiply this row by this column, it would give you the total revenue sold by dealer 2. So that would be a practical answer that we could look at, because that way we could easily see how much revenue each dealer brought in. Now, it would actually be even more practical if you had several dealers. Let's say you have 5 dealers, and then let's say you have 8 models of cars, and I just put in just some random numbers here to show you, how many cars of each type each dealer sold, and then I put in the revenues for the 8 different car models. So if you multiplied these together, when you did this row with this column, it would give you the revenue that dealer 1 brought in, and if you multiplied this row by this column, it would give you the revenue dealer 2 brought in, and if you and so on. Dealer 3 by this column would give you the revenue dealer 3 brought in, and then dealer 4 would give you dealer 5, and so forth. Now actually, I made an error here. This part shouldn't be there. It should just go through dealer 1 through dealer 5. So anyway, that would tell you the total revenue of each of the 5 dealers there. All right, so here's a couple more applications. In this example, the 1999 matrix represents the cost for utilities and insurance for 3 locations for a company, and then the 2000, that's for the year 1999, and the year 2000 shows the utility and insurance for the locations for the year 2000. And then if you wanted to know the total costs for those 2 years, you would simply just add the 2 matrices together, and you would get these total costs by just adding the 2 matrices together. So now this column here, the first column would represent location 1. So let's label this. I probably should have labeled that. So location 1, location 2, location 3, and then the actual rows represents utilities and insurance there. So that would be the cost for utilities. The total cost for the 2 years for utilities for location 2 would be 102, 125, and 142 for each location, and then the insurance costs for each location would be the second row. Okay, now the next question asks you to assume a 3% increase in costs over the year 2000 for the year 2001, and show how you can estimate the cost for 2001. Well, anytime you want to increase something by 3%, all you have to do is take 103% of something. And so if we take 103% of the 2000 year matrix, that just means we're going to multiply that matrix by 1.03. So just multiply each of these entries by 1.03, and that will give you the projected costs for 2001. So here would be the utility costs for location 1, utility costs for location 2, utility costs for location 3, and then here are the insurance costs for each location as well. Alright, I've only got one other problem here. In this problem, we have two matrices. Matrix M tells me how many model A I have of an item. So I have 3 model A's in store 1, and then I have no model B's in store 1, and I have 1 model C in store 1. And then in store 2 I have 2 model A's, 3 model B's, and no model C's. And then this matrix N tells me how much each model, the wholesale value of each model, and the retail value of each model. So for model A, the wholesale value is 100, the retail value is 150. For model B, the wholesale value is 40, retail value is 50. And for model C, the wholesale value is 100, the retail value is 125. So if you were to take matrix M and multiply it by matrix N, you would actually get 3 model A's times the wholesale value for model A in store 1, and then no model B times the wholesale value for model B in store 1, and then 1 model C times the wholesale value for model C in store 1, and then if you add those up, 300 plus 0 plus 100, you'll get $400. So that 400 represents the total value in terms of wholesale in store 1. And then if you multiply row 1 by column 2, that would give you the total value in retail from store 1. So when you multiply that, you get the total retail value in store 1 of the models. And then when you take row 2 and multiply it by each column, the first entry tells you the wholesale value in store 2 for those models, and then the second entry tells you the retail value in store 2 for those models. Now again, I did these with a small number of items on most of these examples, and that's just to show you that you would have, just to show you that you can do these with these small numbers, but in the real world application, you'll actually have a lot more values, because you might have a lot more stores, a lot more model of different inventory, and so you would have actually much more items in the practical applications. Okay, so that covers the matrix operations, and in the next video I'm going to talk about inverses of matrices.